All right, I think I'll start. Hello, everyone, and happy World Computer Day. This is an annual event on the 15th of February each year, where we celebrate the important milestones in computing and the benefits of computers and the people who make it happen. My name is Jim Scherrer, and I'm in Chester County, Pennsylvania, and I'm 1 hour west of Philadelphia, where the ENIAC first was fired up on February 15th, 1946. We use this date, February 15th, in reference to ENIAC. We had the 75th anniversary celebration of the ENIAC in the year 2021, and then followed that with a launch of this event called World Computer Day. So World Computer Day is today, and you see on social media participation all over the world, and you see posts, hashtag, pound sign, World Computer
I think somebody needs to unmute there somewhere.
There we go. Thank you very much. So my name is Jim Scherrer. We kick off 8 speakers for the next 2 hours for World Computer Day 2024. I start with an introduction of a book that we recommend you buy. I'm holding it up here. You saw it in the earlier descriptions.
Jim, with the background, we can't see the book.
I can see that. You can't see the book. But I'll just tell you, it's Tom Haig's book, A New History of Modern Computing. And it's a click link away to purchase on Amazon, which is a nice segue to the author himself. Tom, take it away.
Thanks. Yes, I'm joining you from beautiful Wisconsin, Milwaukee in my little retro computing lab. And I'm just going to share my screen here and get up the slides. All right, so I think that worked. Now let's just kickstart the PowerPoint. So my theme, success and failure, rethinking success and failure in the history of computing. Now, I am just going to zip through this 15 minutes. Then, unfortunately, don't take it personally. I have to run because my class was supposed to start at 4. I'm teaching the graduate historical research method, so the students are patiently sitting and waiting for me to be done. But I am going to catch up with what everybody else says, which I am very interested in, on the recording later. So if you go with the conventional history of computing, as you see, say, in Walter Isaacson's The Innovators, or programs on the History Channel, YouTube videos, etc., then the story tends to be anchored on a fairly small number of famous successes that get described over and over again. And when you write a book like my book, you pretty much have to include all those things, from ENIAC, IBM System 360, ARPANET, Apple II, IBM PC, etc. People who are interested in the history of computing probably know those stories already, but they like to hear them again. And if you don't put them in the book, they're going to be annoyed. So those constantly retold stories become the building blocks for larger historical narratives. And then you have everything else, which tends to be remembered either as a footnote or a failure. So we've got 3 projects this time, none of them, fitting that category of enormous, famous, unavoidable successes. On this map that Jim kindly created, you can see in the greater Philadelphia area, the RCA Selectron, the Philco Transac, and the ENIAC 4. Going to be hearing about all of those over the next 2 hours. And in this introduction talk, I want to just think about what it means a little bit to go beyond thinking about all the other stories, those included as just failures or footnotes. So we've got the 3 projects, right? The RCA Selectron, an initially promising technology quickly eclipsed by other memory technologies, probably would be considered a failure. The Transac, that is not a failure, but it's more of a footnote. It's remembered as the first successful commercial transistorized machine, but not really for anything else. And the ENIAC 4, remembered, if anything, at all, probably for being overhyped and late. So the questions to frame this would include, is the history of computing only about celebrating winners, right? What can we learn by looking at these less familiar stories instead of going over the greatest hits one more time? In particular, something that I think will come out in one way or another from all the presentations that follow, what can we learn from these apparently failed or forgotten projects in terms of pioneering important new approaches, adding context, how does knowing more about projects like this potentially shift the big picture story beyond the way that it's conventionally been told? So I am here to provide some context for those other talks. And in particular, I'm going to talk about how the three projects connect to material in two books that I've written. So the first one, ENIAC in Action, unusual in focusing on a single machine. Now, ENIAC is a very important computer, so ties in with the first draft and EDVAC and other early computing projects. So it gives you a bigger picture, but focusing on a single computer and considering it from different perspectives allows you to have a lot of detail, kind of richness and nuance. And the other book swings to the other extreme. So A New History of Modern Computing came out 3 years ago now. The entire history of computing in one volume from 1943 to 2020. And in trying to compress that and turn all those many stories involved in the history of computing into one big book, then you've got questions about what stories to include and how to weave them together. So I'll be talking about what in those two books is relevant to these three stories, again, to give that kind of context. So ENIAC, famously the first programmable electronic computer, designed and built at the Moore School of the University of Pennsylvania from 1943 to 1945, and then used at the US Army's Ballistics Research Laboratory in Aberdeen, Maryland from 1947 to 1955. Now, in the context of this project, these talks, the most important thing there is the relationship between ENIAC and John von Neumann, who joined the team in 1944 and created the famous report, first draft of a report on the EDVAC. This introduced what's often called the von Neumann architecture and stored program concept. So he talked to Eckert and Mauchly and other members of the ENIAC project team at the Moore School of the University of Pennsylvania. They had the idea, even before ENIAC was finished, that they wanted to produce a follow-on computer. And they also had the idea that it would use a large electronic memory. There's a lot of controversy in terms of who contributed what to the overall idea, but it was first written up by von Neumann. And two crucial ideas there were that the program would be stored not as it had been on ENIAC in terms of the bunches of wire settings and switches spread around 40 panels of a computer that filled a large room, but in terms of a sequence of coded instructions that will be loaded into a read-write electronic memory. That's what's often called the stored program concept, although if you dig into our book, you'll find we don't like that term. The other crucial idea there, and this is relevant to the ENIAC, was a minimalist centralized processor, whereas ENIAC had 20 adding units spread around the room, plus other stuff in other cabinets. It would centralize the arithmetic, and it would only have one adder, one set of arithmetic things, basically one of anything that would be reused in a flexible kind of way under program control. So that's two crucial ideas there from von Neumann's first draft of a report on the EDVAC, which are adopted by early computing projects and fundamentally shape the first generation of modern electronic computers in the second half of the 1940s. And there's a direct relationship between this and the Selectron project. So on the first page of the first draft, von Neumann kicks straight off with the most important thing, which is instructions and how to store them. And as he wrote, the instructions which govern this operation must be given in some form the device consents, punched into a system of punch cards or on teletype tape, magnetically impressed on steel, tape, or wire, photographically impressed on motion picture film, wired into one or more fixed or exchangeable plug boards, this list being by no means necessarily complete. So those technologies had all been used in computing projects up to 1945. What hadn't been done was the idea, again, of keeping the programs and instructions together in a large read-write electronic memory. So ENIAC did not do this, and it would have made no sense to do this, right? So people sometimes talk as if the great contribution behind the modern computer was this idea of keeping the program and data together. But you'd have been a real idiot to suggest that if we were using ENIAC-style memory, because it took 28 vacuum tubes to store a single decimal digit. So for its tiny 200 decimal digit read-write memory, that's the vast majority of the 18,000 tubes in the computer just to store that. You clearly can't scale that up to store the program as well. So with that memory technology, it made a lot of sense to use the switches and wires instead. So in many ways, the modern computer is a thinking through of the implications of what makes sense in terms of a computer design if you have a large read-write electronic memory. And based on that, EDVAC-style computers delivered far more computer power with far fewer tubes. But the challenge was, how do you find a workable memory capable of storing thousands of bits of information reliably for hours at a time and retrieve the ones that you want? And that, more than anything else, is what was pushing the frontiers of digital electronic engineering, a field that barely existed at this point. And that, more than anything else, is why essentially all of the early electronic computer projects were late. And some of them had a period of years between kind of almost working and actually working reliably enough to be used. More than anything else, that came down to the problems of making a memory work. In the first draft, von Neumann considered two candidate technologies in depth. He considered something based on RCA's iconoscope, a tube that had been developed for early television cameras, where the need was to turn an image, record, an optical image into a matrix of points that would be scanned by an electron beam, transmitted through the air, and reconstructed at the far end. Whereas later analog televisions scan continually, this was almost a hybrid of analog and digital because there was a matrix of, glowing points that would be scanned. Von Neumann hoped in the first draft that it would be possible to store 200,000 bits on one tube, which proved not very doable in terms of engineering. So the Selectron is not exactly the same thing. And one of the things I'd be curious to know more about is how much of a through line there is from von Neumann's interest in adapting iconoscope technology and the Selectron that RCA actually produces. The other technology mentioned in the first draft, the one that von Neumann recommended that the EDVAC go with, was proposed by ENIAC co-inventor Presper Eckert, and it adapted radar technology to endlessly cycle a bit train through a mercury tank as a series of sonic pulses. The advantage for that was that almost all the memory storage took place in terms of vibrations in the tank, and you needed only a much smaller number of vacuum tubes at each end of the tank, essentially, to encode and then regenerate the pulses and recirculate them through the tank. So when the UNIVAC 1 was produced, that had 120 characters of storage per delay line times 100 lines as its main memory. But making that work was challenging. It accounted for a lot of the delay on the UNIVAC project. The University of Pennsylvania, which was building the EDVAC computer under contract to the government, tried to make a delay line for ENIAC, and it was delivered late, and they tinkered with it and it never quite worked, and eventually they took it away again. So getting a reliable electronic memory was really the crucial difference between having a working computer and not having a working computer in the second half of the 1940s. For von Neumann's own computer project, though, launched a little later at the Institute for Advanced Studies and extremely influential, he worked with RCA for memory, and they came up with the Selectron, which, as I said, was related to the iconoscope idea. It had a grid of wires, it had an electron gun, and it was intended to store up to 4,096 bits of memory, and it didn't work particularly well. Right, one computer used it. The IAS computer itself was refitted before it was even finished with a third memory technology, Williams tubes, developed at the University of Manchester. I think it used a more conventional cathode ray, relatively reliable storage. And of course, those of you know anything about early computing know that a few years later, all of this was swept away and replaced by core memory, and everyone was very happy. So that's the Selectron. The Philco Transac. So storing programs in memory allowed computers with far fewer vacuum tubes, a reduction of essentially an order of magnitude from the ENIAC to the IAS computer. But the tubes were still bulky, power-consuming, fragile, and unreliable. As you all know, transistors are more desirable in each of those respects. Initially, I think particularly desirable for military applications, mainstream by the mid-1960s. Without the shift to transistors, mainframes would be bigger and less reliable. Mini computers would not be particularly viable at all. So I looked in overview, new history of modern computing. What did we say about the Philco Transac? And that one made it into the book. Unlike the Selectron, although of course we do mention those in ENIAC in Action, it gets this paragraph in that section there towards the supercomputer. And we say Philco contracted with the NSA to produce a fast computer, transistorized. They followed up with a commercial version. And that under delivery of a small UNIVAC computer were the beginning of the transistor era. So it's in there, but honestly, this is text that my co-author Paul Ceruzzi wrote for his earlier book, A History of Modern Computing, and that is essentially all I know about the Transac. So clearly, there is a lot more to be said about it than just it was the first. I know little about what it did or any other novel features it had or who used it and for what, and I'd be eager to find those things out. And finally, the ENIAC series. So the very first ENIAC is in ENIAC in Action. It was a clone of the ORDVAC computer, which is in the book because it, EDVAC and ENIAC were sitting side by side at the ballistics research lab for a while in the 50s, 3 computers that could be used for different problems. And we talk about how they all worked in practice. The ENIAC-2, a transistorized supercomputer, so that's got a relevance with the Transac, although it didn't make it into our book. And the ENIAC-4 highly parallel supercomputer. So that was, I think, the most dramatic departure to date from von Neumann's idea of a single central processor with a single arithmetic unit. Just like those earlier problems with memory technology, the materials and the engineering were a big problem. It was planned to use some kind of cutting edge LSI chip technology, which didn't work. They switched to a different one. It was delivered years late. Then it still didn't work. It took 5 years of tinkering to make it go. It only had 25% of the original scheduled processors and apparently only ran at 50% of the speed. And I only pretty much know that from Wikipedia because I'm not aware of any great in-depth historical articles about this. It's a project that's prominent at the time. People will mention it in Datamation and so on. I come across it, but I don't think there's been any great historical work done on it. And it would be lovely to see more in-depth work done on the history of the ENIAC-4, which was nevertheless still claimed when it became operational to be the fastest computer to date. So none of those ENIACs are mentioned in the New History of Modern Computing. And part of that, again, is as a historian, you kind of reach for what has been written about, what you can find books about or articles in places like Annals for the History of Computing, and they remain underdocumented. So we found basically other systems to tell pieces of the story that could have used perhaps those examples. We talked about IBM Stretch as the first supercomputer and its failure to live up to performance goals, but how it nevertheless had architectural features that were extremely influential later. And if we knew more about the ENIAC-2, maybe that could have illustrated the same points. We talk about CDC as pioneering the success of supercomputers as a product category. In terms of multiprocessing on a small scale, we talk about Multic systems, and on a large scale, we talk about thinking machines rather than ENIAC-4. And in terms of the difficulties of working with exotic materials, we mentioned that in the how supercomputers needed unorthodox physical form factors. We talk about Cray. So, and this is the last slide. Wrapping this up from the viewpoint of a professional historian, I think preserving these kinds of stories and telling them has got great value in broadening history. So the first thing is collecting and archiving papers and records at places like the Charles Babbage Institute and the Computer History Museum provides the raw material for high quality history, right? If papers relevant to these projects get saved and archived, they should still be there in 50 years, in 100 years. You know, historians as yet unborn can write their dissertations on it. If the materials aren't saved, then the primary sources for a good in-depth history won't exist and they may never get written about properly. Second, there's certainly a value to specialized and detailed studies, which don't have to be written by professional historians. IEEE Annals of the History of Computing publishes a lot of well-researched, in-depth articles written by amateur historians, sometimes by people involved in the projects, that begin to pull that material together, gather facts, and tell stories with them. And those kinds of articles in turn get drawn on by professional historians and journalists for other articles and books. So when we try and tell that big picture story for a new history of modern computing, unlike all the in-depth archival work that we could do for ENIAC in action, you can't try and do that for the whole of the history of computing. So we relied a lot, instead of going back to all the original sources, we relied a lot on things like annals in articles in IEEE Annals for the History of Computing. And perhaps if people can preserve those materials, tell those stories, maybe think about writing up some of these stories for IEEE Annals or technical journals, then the next edition of a book like A New History of Modern Computing maybe is going to be able to say a little bit more about Selectrons, the Transac, and the ENIAC machines. So thanks for your attention. As I mentioned, I do have to rush off and teach the class now. If anyone has got, I guess, an immediate right now question, I could take it. But other than that, I'm going to bid you all good luck, and I'll enjoy catching up with it later
Tom,
on.
let me say thank you so much. What a nice introduction and a good broad overview of our 3 objects tonight. You're a treasure to World Computer Day, and you're a treasure to this event. So thank you very much for sharing your time out of class.
All right. Thanks, Jim.
All right, we're going to jump on over to Bob Roswell and the System Source Museum, and he's going to jump on into the first object we're talking about, which is the Selectron, a beautiful mind, a beautiful device, a beautiful thing. Go ahead, Bob.
Okay, good afternoon. I'm Bob Roswell, and as Jim said, I'm the curator here of the Computer Museum at System Source. We're in Hunt Valley, Maryland, which is suburban Baltimore. And we have a lot of physical objects here for people to look at. We're trying to follow the model of the Living Computer Museum and make a lot of things work. Not everything, obviously. I'm joined today by Robert Gillespie, who's over in another room. And we unfortunately do not have any Selectrons, but Robert brought a wonderful collection of them. And also on our panel today will be Charles. So I'm going to share a couple of slides as well. Thomas covered a lot of what I was going to cover. So here we go. We've titled the talk Selectron, a Beautiful Memory, because they are really gorgeous tubes. I learned from Charles's webpage, I guess Selectron comes from Selective Electrostatic Storage Tube. Charles, is that right?
That is correct.
Cool. So again, I'm Bob, and Robert, why don't you come and say hello?
Hello, from the other room.
Okay, and Charles.
Good afternoon.
There he is. So I thought I would show just a little bit. Robert provided a couple of slides. You want to talk about this?
Yeah, I'm a tube collector. I've been collecting for 40 years now. I just brought a couple photos of these are Fleming valves from the very beginning. The very first diode that led to where we are today with transistors, and there's probably about 1 million of these in your cell phone now in your hand. These here are the spherical audions, the very first ones, most popular ones that people know. The Forest came up with the first triode after the diodes. These were came about 1908, 1909. And again, these led then to the development of where we are today. Here's my display cases showing tubes from around the world. These are American, French, German. These are all up to 1920, and a lot of history in each tube. And then left to right, we go through the decades, and the selectrons are on the far right. You can't see those, but we have them here in hand today to be shown in a few minutes.
And I will give you my take, some of which was already covered by Thomas. But my reading of history, and of course, I've been lucky enough to live through a lot of computer history, but having been born in 1957, obviously I missed the first couple decades. But in 1937, Claude Shannon wrote a really important paper. Found it interesting that the picture of it had a signature redacted, but he really described how to build a CPU. And his paper here is called Symbolic Analysis of Relay and Switching Circuits. He did not describe how to build memory. And as Thomas stated, the ENIAC had 20 accumulators. Each one was 10 decimal digits. So by my math, each decimal digit can be represented in a nibble in 4 bits. So we're looking at about 100 bytes of memory for the entire ENIAC. As he mentioned, one of the next ideas for memory were delay line memories. And these came in all different sources. I've been looking for a mercury delay line for a long time. I have to settle with a picture of it. But here in the museum, we have some of the magnetoresistive delay lines. And we've now lent out one of our Bendix G15s for restoration. And Dave Lovett of Usagi Electric has been able to get some readings from the timing circuits of our drum delay lines. So delay memory was actually used in a whole variety of computers and terminals. But delay, of course, is a really bad word for high-speed computing. Basically, we're going to put a pulse in one end of that mercury delay line or that magnetoresistive delay line, or we're going to write a 1 or a 0 on that magnetic drum. But we have to wait until the drum rotates or until the wave propagates. So that's not ideal. Of course, as was already mentioned, von Neumann wanted code and data to reside in memory. He then started to work on the ENIAC computers, and he urged RCA to develop the Selectron. And as was mentioned, the Selectrons didn't last terribly long, beginning in 1951, and then really through the 70s, most memory was done as core memory, as the ferromagnetic cores. And I'm going to shut up and stop displaying. And Robert, do you want to show some of the Selectrons? We set up another iPad with a camera that you may want to pin. We shut off the sound on it because it's in the same room, but can everybody see the Selectron that Robert's showing? If you pin it, you'll see it large.
All right, Bob. Again, my name is Robert Gillespie, tube collector. So what we have here is the 256, which is the one that was used in the actual memory systems. Here's a photo of the Air Force. You can see there's a line, and there's 20 of them lined up here in the top. I happen to be lucky enough to have some of the developmentals borrowed from a collector here in Lancaster, Pennsylvania, where the factory was. Bob Millard met with someone who worked in the RCA factory 10 years ago. The man has passed unfortunately, there's nobody left really. Just ran out of time. So they started with a 9-bit. And this first one, we can only assume RCA dumped a lot of paperwork. So this one's a heads-on. There's 9 dots in there, so 9 bits. And just going on assumption, that was one of the first ones, because then we have future iterations where they're at a slope. There's 9 bits, nine dots. Slope, this one still has an evacuation tip on it. And each pin then would be for 1 bit. Then we go to a heads-on 9-bit. Same pin out. This one's a little more archaic. This one, much more clean. You can start to see the layers behind the 9 bits. There's layers of mica. And the way it works is they call it an eyelet, and it holds the electrostatic charge. And then they question that through a
If I could
pin.
jump in real quickly,
Uh-huh.
the sharing isn't sharing quite right. We have a close-up of your face, at least on my screen, and
Look at the tab
Yeah.
called Bob.
There's one says Bob,
yep.
If
then
you
pin that one.
pin that one, you'll see quite clearly.
Oh, okay.
Is that working for you?
Perfect. Thank you.
All right. So you can see the layers then of the micas, and much cleaner. And from here, it's assumed that this was next in the line. And it's 100 dots, so 200 bits. And there is limited paperwork that discusses each pin was for a bit. And they realized quickly that it was getting difficult to put so many pins through the glass. And there was, somebody smarter than the rest of us, I guess, that sat down and figured out addressing. And they solved the problem of addressing, and they used 3 pins at a time to address one single dot. So they then were able to reduce the number of pins through the glass, not have 1 per bit. And I have here one of the patents. It just shows the layers and the layering through the tube. So the wires would run lengthwise and widthwise. And as a collector, I just don't understand quite how it works, but it's pretty neat. And for a size comparison, we have our soda can here. And no paperwork on it, but as the 256 progressed, the dots, for some reason, the dots would get, we have multiple examples here, until the latest iteration they called a smooth face, where you can't see any of the bits at all, but they would light up and give you a visual representation of each bit as it was addressed. And yes, a blip on the map. Were they 2 years? 2 years that they were the only thing available, and then what came next, Bob?
The core memories.
Core memories right after it. All right.
Although our Bendix computers were still using drum memories, and they were made in the late 50s. So things overlapped with drums and cores, and certainly the computers I was using in college still had core memory, even though semiconductor memory started to come out.
I think a lot of problems were addressed here. Like we're talking about with the grid patterns, you can see that in ferrite cores. So I think there was a lot of ideas developed in the 2 years that they focused on Selectron and had no other options. Over to Charles, I believe.
All righty, I'll jump on in now. I'm Charles Osborne. Let's see, I have to unpin somewhere. You have to excuse me. This is my very first Zoom. And anyway,
There's a
let's,
button called remove pin if you did pin it to see a larger.
and sorry for the delay. Pin, replace pin. Okay, we're back to there. And okay, now I see Bob again.
You should be able to share if you want to share your PowerPoint. You should be able to hit share screen.
All right, so we go to share screen. Share screen, we'll start out. PowerPoint, share.
Got it.
Got it? All righty. So we're going to discuss the ancestry. So we have to go back in time, way back, not caveman troglodytes, but back to the period between World War I and World War II, when airplanes became a threat by not falling on you, but by dropping weapons on you. And so we are looking here what's called a gun director. These were mechanical computers designed to replace dead reckoning and sharpshooting to try to shoot aircraft that are coming in with their lethal payloads. They were mechanical single task computers built entirely mechanical construct. They were gears and cams, cam followers, motors, ball and disc integrators. And that's because that's pretty much all they had at the time. And you can see right here, we've got people looking into telescopes and they got their hands on knobs. They're trying to keep crosshairs on top of the incoming aircraft. Other people who are controlling things such as the current windage that's predicted. And so we wound up with these mechanical gun directors. They were better than dead reckoning, but they weren't all that great because you've got an aircraft flying in overhead and you have all of these operators are entering into this director with the plan of setting the time on the fuse and then aiming the gun and leading in front of the incoming aircraft. It was better than dead reckoning, but not by a whole lot. Back in the 1940s, one of the engineers at RCA Laboratories by the name of George Morton said, maybe we can do this electrically. And RCA was at that time one of the leading organizations for the use of electronics and the use of vacuum tubes. And so Morton said, we can do this better. We can do it in a digital way, not an analog way, where you've got different voltages and different angles and different levels, but we can do it digitally using this new digital computing technique. And being with RCA, they were extremely ambitious. George Morton, whose boss was Vladimir Zworykin, said, we should be able to do this 5 men for 6 months for $35,000. We should be able to come up with something to replace that giant mechanical monster. The war was coming and the exuberance was there. Took about a year, and I apologize to those of you who do not have the 6-foot diagonal Microsoft Touch computers. This is a block diagram that they came up with in June of 1942. And I'm not sure you can see my cursor, but on the far left-hand side, you've got shaft encoder inputs. These were essentially replacing the 3 people on the left of that first photo. If we go back up here, you got the 3 guys on the left inputting information. That is the information that is now coming in, but coming in a digital fashion, not an analog fashion, not potentiometers. These were 14-bit shaft encoders that were designed between RCA and Eastman Kodak. The digital information then went over to these particular structures here, which cannot get into great detail for time purposes. These were called computrons. This was something else that came out of RCA Princeton. This was a single tube, a single vacuum tube that could multiply two 14-bit binary numbers and get a 28-bit result in one vacuum tube. That's a different story about a beautiful device that didn't come to fruition. Moving over to the next column, you see these frying pan, panhandle looking devices. Those were the iconoscope memories mentioned earlier. The iconoscope was something that was developed by Zworkin and his team originally at Westinghouse and then at RCA when he jumped over. It's a very simple device. You project light on the front. You've got a little storage plate with little photosensitive capacitors on it. And you've got an electron gun that you can magnetically steer the beam and interrogate those little capacitors and see which ones are bright, which ones are dark, and make a video signal. This was the first commercially successful television image pickup device. Looks simple. If you look at this window here is actually about 3 by 4 inches. Yeah, you could probably store 200,000 bits on there, except you can't because you're storing it as little piles of electrons storing as a charge, and they tend to bleed off. The external magnetic fields tend to deflect the beam to where it's not supposed to be. The implementations never really worked out really well. So the people at RCA said, we're going to go straight digital. We're just going to jump right on in and take and reduce all of the analog to digital. So now instead of having one electron beam that goes out and hits a spot on the wall to interrogate the charge or deposit the charge, we're going to set up 64 columns and 64 rows of wire bars and wire discs, and we'll spray from the center of the tube out simultaneously around the entire device. This was supposed to be 4096 bits, which seems to me to be a combination of hubris and expectation, delivering expectations to have the first one out of the gate be 4096 bits. When Bob had mentioned earlier, EDVAC only had a few hundred bytes. So this one worked. It didn't work all that well, but you have to remember we're in the early 1940s. This was an incredibly complex device to build. This is one of the mica drawing for one of the mica sheets. We'll go back up to the top. One of these mica sheets that hold all of these mechanical things in place. There is no computer-aided manufacturing, much less computer-aided design. These sheets of mica, which for people born in this century, is a glass-like insulating material, so you can hold things around without having electrically shorting. These had to be punched out using the machine technology of the 1940s. Just staggering concept. But they were able to build a couple of them, put the plates on the outside, phosphide layer on the inside to hold the storage charge, and build a couple. As a close-up that shows the incredible detail and the amount of manual labor required to build these was just phenomenal. But the performance was too low. The spacing between the columns and the rows was so small that the electron charge would bleed out. It didn't work. They did a bit of overreach on the first attempt. So they decided to let's take back and store the charge on discrete metal eyelets. So instead of having the spaghetti thrown against the wall and hope it sticks and doesn't slide down into the next spaghetti blob thrown at the wall, we're going to have individual pots, individual little containers. So what we have here is a metal eyelet, which has sort of got a shallow end and a deep end made out of steel, and it's held in place with holes in mica, again, keeping it insulated. So now instead of hoping the charge doesn't leak across the phosphor, they are physically restrained into these individual eyelets. That's the structure that eventually wound up being used. I believe Robert we could probably show a couple of pictures a little bit later, has one of these. I also have a 1024-bit. Eventually, they kept making the eyelets bigger and got the signal to noise ratios up, so they were able to come up with the 256-bit SB 256 Selectron. The signal levels were still so low, they had to have coaxial connectors through the base of the tube itself, because you're switching hundreds of volts to gate the signals in and out. The signals that were being the output were getting swamped. Now, to just go off the chart a little bit, the grids and columns are set up that you open a window by putting positive voltage on two adjacent columns and two adjacent rows. This would allow the electrons to flow out to the phosphor screen for either writing or interrogating. This way, you had a 4-input AND gate for each individual memory cell. So it was partially decoded. And as Robert alluded, some really clever people back at RCA Princeton, the David Sarnoff Research Center, were able to figure out we can use this to reduce the number of pins by having the addressing scheme partially hardwired in. And this was also done by George Morton, the person who originally decided to try to pursue it. And this work was all done at the RCA laboratories in Princeton, New Jersey. There's a picture, an earlier picture, and a little bit later one after it had been redesignated the David Sarnoff Research Center. And since I've got some people on here from Sarnoff, I have to be a little careful with this. Just as a matter of background, here's a picture from an unspecified number of years ago of the reading room in the David Sarnoff Library, an area which I was told and nudged. This is not a photographic area, but it's your standard 1950s. We got the big picture of the president of the company, David Sarnoff. We have the Hall of Old White Men having their pictures on there too. We had the big, beautiful fireplace and the soot that came out because one time somebody turned the fireplace on and forgot to turn on the exhaust fans and filled everything with soot. But there's another photo of the library surreptitiously taken, and one more photo. And just as a reference, the lighting has no bearing at all of cathode ray tubes. If you think you see cathode ray tubes as lights shining up onto the ceiling, it's purely your imagination, in the same way that the Columbia Records building in Los Angeles doesn't look like a stack of records. It's purely your imagination. Now, a lot of the heavy lifting for building the Selectrons, and they only built a few hundred, there were only two design wins. One was the ENIAC computer at RAND Corporation in Santa Monica, and another for an Air Force Cambridge Research Center project back east. Those were done at the RCA Lancaster facility, which was built by RCA during the Second World War to build all of the electron tubes needed for the war effort. After the war, RCA purchased the facility back, and this is where the development of cathode ray tubes, color television, a lot of technology came out of here. Jumping ahead just a little bit, here's an aerial shot of what was called RCA Lancaster. If you look over here, just a little bit off dead center, you can see little yellow pixels. Those are school buses, to give you a concept of how big this facility really was. There was a discussion about why the Selectron failed. Well, it failed because it was too slow and it didn't outrace the magnetic core, which was kind of co-developed between RCA and MIT. There's a lot of people in each camp can present information that they were the developers of it. But at RCA in the late 40s, early 50s, television was king. And in the 50s, when the Selectron was really trying to make its push, compatible color television was the 800-pound gorilla in the room. And combating CBS was more important and ate up resources more than this digital computer stuff, as evidenced by another surreptitiously taken picture of a few of the Emmys that the engineers and scientists at Sarnoff have won over the years. So the Selectron was a bit of a red-headed stepchild, and it suffered from failure to thrive. And if I can switch over to a different image, I can give you a picture of what, if I can get up there, a picture of what it used to look, what a Selectron would have looked like. Let's see, get rid of that. Come back up here, share screen, up to here, share. Sharing screen is stopped as the shared window is closed. Okay, I'm not sure what that means. Looks like it's sharing it to me. But anyway, if a Selectron were ever to be powered up again, you could actually have a visual representation on the screen of the bits which are at 1 and the bits which are not. And just as a brief homage to von Neumann, who is also a fan of the game of life. I've put a couple of patterns up here to represent motions of the game of life. So that pretty much covers my part of it. Go ahead.
What was that, Jim?
That's about it. So I'll throw this back to Bob.
I'm good. Robert, you want to just put a couple back up on the picture called Bob again? Because I think some people didn't see it. If you pin that, you'll get to see them up nice and close. Beautiful.
Biggest tube I've ever seen.
No, Robert also brought what a much larger one that was you can show that too.
Right, there was discussion of the iconoscope, which was the image saving tube. I brought an early Zworykin iconoscope here. If you look at the Robert Gillespie pin, it's huge because at the time nothing was small.
And of course, none of these hold a candle to a CRT.
No.
Yeah, I was going to say a 27-inch CRT blows any of these things away, but we don't think of them as being the same.
All right, let's jump on over from the Selectron to the next topic. We could call this halftime. It's now 6 o'clock. We advertised this to run for 2 hours from 5 to 7. And we have 3 objects. We've only covered 1, but it was a great deep dive into the Selectron. I'm really impressed with what I saw. These are beautiful devices. It's an amazing thing that they were able to create them without all the advanced manufacturing techniques that we have today. Paul Kizivat is going to talk to us about the Philco, and that'll be followed up with Bill Mensch, who did work at Philco Research. And both of them will introduce themselves and do a deep dive into the Philco line of computers. Go ahead, Paul.
Hi. We're jumping ahead in time quite a bit here, and technologies. As Thomas said, those early things that the core came in and replaced most of these earlier technologies. It allowed a lot more bits, and that gradually came in. And as he showed, the Transact. We also had the transistor revolution, and the Transact was the first, transistorized computer, which I believe started about 1958. Now, I'm not going to give a hardware talk because I'm not a hardware guy. I'm a software guy. And so I come in 1967. I just graduated from college and I went to work for Ford Motor Company in Dearborn at their engineering center. Now let me share here. See if I can not fat finger this. See, did that work? Can you see my slides?
Yes, sir.
Okay. Now if I would stop having trouble with my screen, just lost my screen. What happened? There we go. I don't know, something happened in my. There we go. Anyway, well, I arrived at Ford in 1967, and what I found there was that they had a Philco 212 computer, which was the current incarnation of the Transact project. I believe that there was an earlier one, and I heard a lot about 58, and so I think there was a 211 or 210 in 58, and then a couple generations after that to arrive at the 212. Now, I never really heard exactly why Ford had the Philco, but I suspect it has a lot to do with the fact that Ford bought Philco in 1961. And I don't know how soon they got the computer after that, but it was certainly well established when I arrived in 67. And compared to the things we were talking about earlier, this is massively more powerful than those things. It had 32K of 48-bit words of core memory. Now, this took about a rack to hold, as I recall. It had 16 magnetic tape drives, and if people that believe they're familiar with the old things they see in movies with the spinning drives, most of those were half-inch drives. They eventually got standardized. These were kind of weird ones. They were 1-inch tapes. And at the time, on the Philco, this was the only real means of input and output to this computer. And it let's take a look at it. You've probably seen things like this on in movies before. What you were seeing was probably an IBM system, or maybe if it was an old picture, maybe a UNIVAC system. But this was the Philco. You can see all the tape drives. The big thing in front is the console that was run by the operator. And the unit in the middle behind that is the CPU. You can't really see the scale very well. It's about 6 feet tall, about 12 feet deep, I would say. Many racks. And I don't even know what the stuff on the left is. And the system was used in a batch mode. I mean, it's better than the earlier computers where it was hands-on for whoever used it, I guess. But this was the time when the users couldn't actually access the computer directly by themselves at all. Users created their programs on punch cards at a key punch. They then assembled them into a stack of cards that described the job they wanted to run, and they turned it in at a computer at a window to the room where the computer was. Operators collected input from a bunches of users until they had enough to be worth the trouble of doing something with, and they put them through a card reader and onto a mag tape. This was supervised by another small media computer. I don't even know what kind that was. And then they would walk the tape from that thing that has the input jobs on it over to the Philco 212, and the operator would hang it on one of those tape drives and then push some buttons on the console in order to cause the operating system to start reading input from that and processing it as jobs. The jobs were single stream, run to completion, and whatever you did, if you did a compile, you got an output that listed all your compile errors or something like that, plus a listing of your program. If you could include data in your stack of cards, and then so you could run your program after it was compiled, and it would read the input that you would supplied on cards, and then it could produce printed output or punch card output, which was in turn written to another tape. And then the operators would take that tape and they would carry it back to the media processor, and that would like spool all the printed output from the tape onto a big line printer, and with the fan fold paper and all that stuff. And that was how work was done. So for a user, you would turn your stuff into the window, and then you would go away and you would wait a while, hours probably, and then come back and find your output. So it wasn't very speedy mode for program development or program operation. And of course, there was the uncertainty. You didn't know how long you had to wait. But it was what it was. And I think compared to the alternatives, people accepted this. And this wasn't unique to the Philco. I mean, pretty much most of the computers of that time operated in more or less the same way. I mean, the details were different, but the mode of operation was the same. Now, from a software perspective, how did this work in this thing? There was a batch monitor program, an OS we would call it today. It occupied the first 4K words, which is 4 times more like 16K bytes, if you like, of memory. And then the remaining memory from 4K up to 32K was used for user programs. There wasn't any memory protection. So, an errant user program could clobber the OS. And that was not an uncommon thing to have happen. When it did, at some point, the operator would realize something was wrong. And then he could push buttons on the console to force the system to reboot. And then it would just start over. It would just pick up with the next job on the tape. How would the operator know? Well, there was, the console was very elaborate. It had a bunch of displays. It showed what instructions were being executed and so on. But even more interesting was that they had taken a loudspeaker and wired it to the address, the program counter address line and it would play out tones based on the pattern of memory references. And you'd learn to recognize what was going on. You know, if the program got into a repetitive loop that was consistent over time, you would hear that as a pattern. And if you heard it long enough, the operator would just say, program busted, and would force a reboot. So that was what things were like. How did things get programmed? Most of the programming was done by the engineers themselves. As I said, this was the Ford Engineering Center in Dearborn. This is where all the cars were designed. There was no such thing as professional programmers back then. So this was mostly done by the engineers themselves, typically in Fortran. And as I said, people accepted it, but this was cumbersome and not very efficient. And people wanted something better. So there were things in the air, of better things. They weren't widely available, but they were out there. MIT had a 30-user time-sharing system on an IBM 70, 90, 94. I don't remember. It varied over time. I was aware of that. I was at MIT before I went to Ford. I was aware of that system, but I never had access to it. The undergrads were using a batch operating system like I've described, but on an IBM computer. So that was experimenting. MIT was also getting ready to do Multics, but that really hadn't started yet, except in theory. MIT also had a 3-user time-sharing system on a DEC PDP-1. It was a tiny computer. But it was just a university creation. It was nice for students in a class. That was the first time-sharing system I got to use, I believe. And I think the most successful of the bunch was that at Dartmouth, they built a 30-user time-sharing system on a GE 635, 265 computer. Interestingly, there was no computer science back then, and certainly they didn't have any graduate degrees I don't think for scientific things. I think either. The system was developed at Dartmouth by undergrads and some faculty. And that's where the basic computer language was invented. And they at least had a system that they let all their users use. It was like a 30-user system. So those were the kind of things that people were aware of out there that they wish they could have. Turns out that finally that GE, that Dartmouth system got productized, and Ford got one in probably the year before I arrived. So that was made available to engineers as well. But it was kind of a toy. The programming was just in BASIC. The programs that you could manage, that you could realistically run, were small. The computer was slow. So it was kind of like a teaser. People could see, hey, this would be cool, but I can't run my real work on this. I need something better. So they wanted a better time-sharing system that would run the kind of Fortran we were used to and support more users and longer running jobs and stuff like that. So at the time, they looked around and there was really nothing you could buy. Well, you could buy the Dartmouth system, but it wasn't enough. And there really wasn't anything else you could buy at the time. And so the decision was made that Ford would build its own time sharing system to run on the Philco 212. And that's why I was there. I mean, I was, they decided we're going to have to hire new people to do this. Yeah, and it's gonna be a project. So, I mean, I was kind of an add-on because they hired people from Dartmouth that had done the Dartmouth system. And the end, there were maybe 6 to 8 of us. And so we had to do some work to make, to prepare this Philco system to be able to support that sort of a time sharing system. So we were able to double the memory to 64K words. That was the machine had been originally designed for 32K, but there was like an extended addressing mode that allowed it to address 64K, although it took special programming to do it. There was another, we had to get another computer to do the terminal processing. We got a Philco 102, which I don't know too much about. I think it was another part of the Transact program. It's a smaller computer. And telephone lines, to make it work. And as I said earlier, the batch system was pretty much all tape based. There was no mass storage available to users. And to run a time sharing system, you needed a place to put files and need a place to swap and so on. So we need to get a disk. And as we've seen in the earlier stages, storage of all sorts was a problem. And disk storage was mass storage beyond memory. And we solved the memory problem with core for a while. But for the other mass storage, it was still a problem. And so we were able to get a 100 megabyte hard disk drive, which was huge at the time. And here you can see it. I pulled this out of an ad I found for this disk to give you a sense of what kind of thing we're talking about here. To get 100 megabytes, it had like 12 disk platters that were 39 inches in diameter. Like, I have this one in my house. The reason I have it is because this disk drive wasn't all that reliable. It had a tendency to have head crashes. And when it had a head crash, they had to disassemble the whole thing and refurb it, which took several days, maybe a week, which when our computer system would be down, which of course wasn't ideal. And so this platter was one that was damaged in a head crash, and I took it home. I've had it ever since. So I've been talking to the other people that are on this, and there's other disks of the time that were of similar scale. Obviously, later on, it changed a lot. Anyway, once we had assembled the hardware to do our system, then there was just a small matter of software. Again, we took like I said, we had the people that had done the Dartmouth system, and I believe that was all done in assembler. And another thing that was in the air at the time was maybe you could use higher level languages to do things other than scientific programming. And so we made a decision that we would program this operating system in a higher level language. Fortran really was not suitable for system programming for OSs. You couldn't really manipulate addresses and things like that. So we chose another language that was available at the time called MAD. stood for Michigan Algorithm Decoder, developed at the University of Michigan. Was ported to the Philco by another guy, by a research scientist at Ford. It was, making this decision was pretty radical at the time. Most places that were doing, programming for OSs were still writing them in assembler. And as I said, we had like 6 or 8 people. Yeah. Again, there is no such thing as a professional programmers. There is no such thing as a software engineering, degree or a way to study it. If you wanted to study, you studied math or electrical engineering. So these are just assorted people that had, learned the craft. The system we built, the architecture mimicked in many ways the Dartmouth system. Not in the programming language, and obviously not in the hardware, but terminals were connected by dial-up to a front-end processor, in which case was our Philco 102. It would not, would collect things by lines and then, assess whether the line was a command or data. This goes back to the arrangement of BASIC, where every line had a number, and so if you're entering things, the lines that started with numbers were data, and lines that didn't start with numbers were commands. And the front-end processor buffered the data until it saw a command, thereby not interrupting the main CPU too much. Then eventually, once command was entered, it would basically initiate a job on the Philco 212 to handle the command, and it provided the data to it. So this way, between the issuing of commands, you really had nothing running in the Philco 212, which helped with the load. The active programs that were running shared the 212 resources, and like eventually, it was new at the time, but it was time slicing the CPU among different programs, and swapping programs in and out of memory onto disk. And the architecture of the 212 was such that there could only be one program in memory at a time. There was no memory protection to protect between them. And there was no address relocation that will allow you to put something in memory other than at the place it was designed to run. And so in our design, the user programs used the whole first 32K of memory, and the OS got to take the whole upper 32K, which is convenient because most of the user programs didn't know how to use the upper 32K. And I can't remember right now. I think there might have been an actual memory protection that could keep them out of the upper 32K, but I'm not absolutely certain. Well, this was all a nice idea, but in the end, it kind of didn't cut it. Maybe we should have foreseen this, but it really didn't support enough users. I mean, we could run bigger programs and stuff like that, but in the end, it still only supported about 30 users, and there were a lot more engineers that wanted to use it than that. And the hardware, it was a lot. Like I say, a lot of it was the hardware. It's, you couldn't keep multiple programs in memory and protect them from one another. So every context switch required a swap in and a swap out. And that really, makes you run at the speed of the disk. And as I said, the disk sucked. It was big. For the time, it was fast enough, but it wasn't reliable. At the time, it became obvious that if we wanted to make this viable, we needed better hardware. We actually talked to Philco about it. I was of the impression that they were actually considering making a follow-on to the 212. At the time, I was of that impression. But then they decided not to. Some other reading I've done in the process of getting ready for this talk leads me to believe that they couldn't have really been serious, that they'd already decided to get out of the business even before this happened, which is disappointing to me. I wish we'd known that sooner. So we had to decide what we're going to do next. And ultimately, time had moved on. It was like around 1970 then, and the commercial world had progressed. There were things that we could buy that at least on paper looked like they would suit our needs reasonably well. Mostly it was a con job at the time. They didn't really. But we bought the best of what we could find, which we knew wasn't good. We knew it wasn't good enough, although we didn't know how bad it was when we bought it. And then we spent the next 10 years or more, doing our own modifications, to a commercial offering in order to give us the time sharing that we wanted. And
Well, let me interrupt here and say how wonderful it is that you were actually there on a Philco machine and taking the time to speak to all of us about it, because you're a rare bird. It's hard to find anybody who actually had their hands on a Philco machine. If you can unshare your screen, I'm going to jump over to Bill Mensch, who is in Philco research. He's going to introduce himself and what he did do at Philco. Recall that this is Lansdale, Pennsylvania. You saw the map earlier. So we're geographically close to Philly. I'm always amazed how people crossed over from one project to the next, and they were all geographically in southeastern Pennsylvania. You're listening to World Computer Day 2024, and I'm Jim Scherrer. We have a half an hour to go in a 2-hour show. We may run over, so I'll caution each speaker not to go too long, maybe move right along. So I introduced Bill Mensch, who's in Arizona. Welcome, Bill. Go ahead.
Thanks, Jim. Thanks for the wonderful history lessons. I have a question for Paul, actually. Someone that worked on the 6502 back in the early days actually created the development system. His name was Larry Hiddle. And Larry Hiddle worked at GE. And I think the first, maybe I have the numbers wrong. I thought he told me at one point, now he's gone, so he's not available. But Larry designed and commercialized the first computer terminal called Courier Terminal. I don't know if Computer History Museum was looking for a Courier Terminal, but Paul, I'm wondering if Courier Terminals were used with what I thought was a GE 225 at Dartmouth, because he helped create that time-sharing system. Do you remember? Do you remember?
I can't. The name just barely triggers something in me, but I'm not familiar with a Courier Terminal.
Okay.
We initially used AT&T teletypes, Model 33 and 35, on both the GE system and the Philco system. We eventually moved on to IBM Selectric 2741 terminals. But I can't say I've heard of the Courier. I know
The
I went to
the
I
Courier
eventually
used
went
the
to work for
CRT. The Courier used the CRT.
that must have been later. There were no CRTs at this time.
Well, this would have been early 70s, maybe late
Okay,
60s.
well, yeah, that's kind of after my time here.
Oh, is that right? Okay. Well, I'll move on to my talk. I
Okay,
had never knew anybody that knew about the GE systems and time sharing and
well, you can talk to me afterwards if you want. I'm happy to talk about GE. I worked for GE for a while.
yeah, that's awesome. So did Chuck Peddle, he was somebody that's involved with the 6502. But let me, I guess I can just share my screen. I'll do that. I don't know. Share. PowerPoint. Okay, so I'm going to share my screen, but I first wanted to, because of all these history lessons and all this wonderful information, and I can't believe the engineering that got us to where we are today. And this picture right here, will that come up? Come on. There you go. That's an interesting picture. And I'm starting with this because I'm actually connecting. Oh, I guess I hit it twice. I guess I'm connecting with the, there you go. I'm connecting the past with what I'm going to talk about, which is actually taking from Philco forward. And I just wanted to tell you that I was an advisor to both the College of Engineering at Temple University and the president, David Adamany started the first President's Advisory Board. And one day when I'm visiting Temple on, let's say a few days advising, etc., I had just in the Temple Review or whatever it was called, they had a multi-page, maybe 3 or 4 pages on the American Philosophical Society. Now, as it turns out, one of the people that I was close with, now he just passed away in the last year, his name was Vic Schutz. He was the dean of the College of Engineering, and that's how I got reconnected with Temple. So here I am for an advisory week, and they asked me, Jim England was the vice president there. My wife Diane and I visited there. And Diane is who took this picture. But anyhow, so they asked me, well, we have the afternoon off. Would you like to see anything? And I said, yeah, I'd like to see the American Philosophical Society. And they go, really? Where's that? I said, well, it's next to Independence Hall. It's the next building to the east, to the left, facing south. And I said, so I'd like to visit that. And they go, okay, well, Vic Schutz didn't know anything about that. Vic Schutz advisors were the designers of the ENIAC. And so we go down to Philadelphia, down to Independence Square there, go to the Philosophical Society. And the reason why we were encouraged by the guy in the middle here to come down there by 2:30 because he leaves to go home at around 3 o'clock and he wanted to meet me. And I'm thinking, what? The director of the American Philosophical Society wants to meet me? That's interesting. Okay, well, let's get down there by 2:30. So we get there, and basically there's only one person there, and this is Annie, who is on the right. And so we knock on the door. We had called ahead. Jim England, the vice president of Temple, called ahead. And so there I am. And there's a desk, there's a sitting area in front of the desk. This is the executive director's office that's not Ben Franklin behind there. That's somebody else that was an important philanthropist for way back when. But the American Philosophical was started by Ben Franklin in 1743, the birth year of Thomas Jefferson. So what happens is we go down there and he wants to talk to me. And I'm thinking, okay, well, I'm happy to talk to you. He had a bunch of questions. And in the middle of one of the answers, he said, when I was in computers, and Annie was sitting across the table from my wife and I look at him, and then went back to answer his question because she recognized I didn't know who was asking me these questions. All I knew, he was the executive director of the American Philosophical Society. And so then we're going up after we had our conversation, and he said, when I was in computers, and I'm thinking, he's too old. This is like 1995, 96, something like that. So we're going up the stairs to the second floor to see some of the memorabilia, which is really fascinating. And if you've never been there, they usually don't let the public off the first floor. Now, these days, you don't go off the first floor. So we're going up the steps, and Vic, it's Annie leading us. Vic Schutz, he got his PhD from Penn, as I mentioned. Then it's my wife and me, and she stops the four of us from going up to the second floor. On the steps, she says, well, you know who you just talked to? I go, yeah, Herman Goldstein, the executive director. And then she says, you know who he is? Well, yeah, he's the executive director. Did you ever see a picture of the ENIAC? And I go, I did. I have. Well, you just talked with the army officer that's in that picture. Oh my gosh, a missed opportunity. Oh my, no, I can't believe it. Let's do a do-over here. Anyhow, that's how this whole thing is connected. And so then we went up on the second floor and we saw Ben Franklin's first battery and things like this. But I just wanted to connect that history to what I'm about to talk about, because here I am in the presence of an icon, someone that's amazing. And by the way, the original drafts of the Declaration of Independence, the original drafts of von Neumann's papers, they showed to us because we went over to another building there where they have 5 floors of archives of all the stuff. And that's where the meetings are held. And so anyhow, I just thought I'd connect in that past that you're quite familiar with this guy who is amazing. So I'm going to go now to my slides, if I can find them. Where are they? Okay. Slides. They'll go. There we go. I don't know how to shrink this down right now. I guess I click on it. Yeah, so
just click onto the slideshow.
Slideshow, does it say slideshow there? Where's the button for slideshow? Pardon?
Have your mouse go to the bottom right, and you'll see a screen. Bottom right corner there, a couple of icons. No?
Oh, here? Oh, there,
Okay.
slideshow. Oh, slides.
No.
Slideshow, there you go. Okay,
There you
so,
go. Good.
all right, so Philco Computers, that's what the Jim wanted me to talk about, because I did work for Philco Ford. And what's interesting is that there's one of the hot buttons that Jim put in the call for speakers had this this information about Philco Computers. Now, as it turns out, I don't know, how can I get out of this thing? Back to slideshow. Sorry about this. I'm in areas that I'm not used to being in. Yeah. Okay. Anybody have a hint for me to how, oh, here it is. There we go. So, okay, so anyhow, learning about Philco computers, which I did not know even existed when I worked there at Philco Ford in 1967 to 1969. So this is the time when, after I graduated from Temple, I'm a technician. The highest degree Temple gave out was an associate degree in electronic engineering technology. So I'm a technician working at Philco Ford in Bluebell in 1967 for 2 years. And so this is where I find out that Ford acquired General Microelectronics in Northern California. And that's where I ended up working on a jet engine controller for United Aircraft, which is the background of United Airlines today. So I found out about a lot of interesting topics because of Jim's request that I talk about Philco Ford. So then I'm going to bring this to 6502 computers as a close out of my talk. So as we all know, and as you've heard a lot about the birthplace of the digital computer being at Penn, then I'm finding out that Philco stood for Philadelphia Corporation. That was where they came up with that name, which is an interesting, I didn't know that when I worked for them. So Jim wanted me to talk about the computer transistors. And so this reference document, which Jim connected me with his request, I found out about this surface barrier transistor. Now, I never worked with a surface barrier transistor, but if you look at it, in 1954 is when that came into existence. Now, you know that the vacuum tubes that Penn used for the ENIAC, and all of those vacuum tubes that I just saw, the engineering went into all of those early computers is amazing. And that is the reason why I think Herman wanted to meet me, because he's thinking, oh my gosh, these computers that he worked on, this is where we'd have a totally different conversation if I knew who I was actually talking to. So when I hear and I see all the engineering that went into all of those wonderful systems back in the day, trying to figure out how to make something, small transistors, starting with tubes. I don't know if you know this, but everything in here is field effect transistors. A vacuum tube is a voltage controlled device, and all these transistors in here are voltage controlled, and that's why we get such high performance, because you can actually turn it on and turn it off much quicker with a voltage controlled transistor rather than a current controlled transistor, which was what the surface barrier transistor was. It was very innovative. I don't know really how it works, although I saw that it was like a Schottky diode where you have a metal and semiconductor, and that can have a low voltage to turn it on and turn it off. But the surface barrier transistor is what I think ends up being a current controlled transistor. So now, if you look at the size of the transistors compared to the vacuum tubes and the actual amount of power to turn them on and turn them off, was a major invention, major contribution to the industry that we have today, because at that point, Philco knew we had to go to transistors away from vacuum tubes, and they got us started in that path. Now, in 1965 is when I was at Temple University. So I started there in 1963. So I was there in 1964. Then 1965, my aunt suggested this guy that she knew from IBM, George Rogers, was a friend that would stop by her little convenience store at the intersection of 113 and 611, which becomes, as you know, Broadway. And that's where William Penn is on the top of City Hall. When I was visiting there, doing some work there to get gas for my little sports car, she says, hey, he's out there. Go out there and ask him what you can do when you graduate from Temple. I went out there. I said, my aunt owns a store. She thinks you might have an idea. And his thing was like in The Graduate, the movie The Graduate, where get into plastics. Well, George says, get into computers. So that's one piece of advice. I'm a middle child. My mother had 10 children. Nobody in my family. I'm a first generation student. So I didn't really know what I was getting myself into. But when I got this one piece of advice from an interesting person that was introduced to me by my favorite aunt, I'm taking that advice and I'm going to go with it. So at Temple then, in 65, 66, I studied analog computers and basic functions of analog computers. And that was my senior project, graduating in 1966. So then I worked for a small company. I usually don't say this, but for 3 months after getting out of the basic training, I was in the National Guard Army. I wanted to avoid going to Vietnam, but you know that National Guard was actually what we need to prevent us from burning down our cities and stuff like that. So I'm in the National Guard. And so I come back and my fraternity brother found a job at Polyphase. Polyphase is a company in Bridgeport, part of Norristown. And I worked there for 3 months for $85 a week. And I was working for Hinkles and McCoy while I was going to Temple, making $150 a week. So here I've got my associate degree, working for about half of what I was making on a construction crew or a landscaping crew with Hinkles and McCoy. And just like some of these people said, well, you're not going to be working in whatever you're going to college for, because I don't know anybody that goes to work in what they learned in college. And these are people that didn't go to college. So there I am. When I didn't get my raise at 3 months, I quit. I didn't have another job. I just quit. I didn't want to be there. It was the wrong place. And then 2 weeks later, I find this ad, and that's how I ended up working at Philco Ford. And so I was working at the Advanced Semiconductor Lab there in Bluebell, and that's where we were analyzing all kinds of transistors. And one important transistor at the time was a power transistor for alternators. So Ford was early in getting electronics into automobiles. And so I was analyzing the thermal coefficients of power transistors so they didn't burn up. We had to heat sink them and other things. And then the other thing that I was introduced there, which was a jet engine controller. And the jet engine controller used the GME 1024-bit ROM chips. They were MOS and GE microelectronics that Ford acquired and then tried to move some of the engineers from the West Coast to the East Coast. Well, that didn't work out so well for many of them. But anyhow, I'm working on this jet engine controller that's a single board computer, 15 layers of printed circuit board. It costs like $35,000 for one board, unpopulated. And then this board, we had 3 or 4 of the boards, and this was going to control the jet engines of United Aircraft. And so they were having problems. It wouldn't work to 125 degrees C. It would stop working at 100 degrees C, and then the engineers would tell me what to change about it because I had good eye-hand coordination. I was the only person that could ever make any changes to the board, so there was nobody else going to make any changes. The engineers but they gave me that responsibility, which is quite interesting. So all of these things, they'd come back, they'd go up and visit. What's the problem? They would have to report to United Aircraft. And when 1 week they said, okay, if we don't figure it out this trip, they're going to cancel the project. And I'm thinking, well, this is my project. I'm working on this with this engineer. And so everybody left for Connecticut, United Aircraft. And there I am on a Friday, and I'm thinking, well, why don't I just try to figure out what's going on here? So what I did is I soldered a wire on the main signal, with the main clock signal, and I raised the temperature, and sure enough, it flatlined at 100 degrees. And I'm thinking, oh, that's interesting. So I just found the main clock signal doesn't work, so nothing will work. So then what happened? I think, well, what's there? It's a 10 picofarad capacitor. I'll get a 10 picofarad, double the capacitance. I'm wondering if that'll change anything. Sure enough, it fixed it. But then I want to celebrate. Nobody else knew it. Hey, they're all in Connecticut. And so then what did I do? I had to wait until Monday. Oh my gosh, that was a long weekend waiting for them to come back. They come back and they said, we found the problem. Oh, you did? What's the problem? And say, this is the chip. We need to change this chip right here. And I looked at the chip. It wasn't anywhere close to where the one shot was for the main clock source. And so the leakage current is what caused it to flatline at 100 degrees C. I said, well, I don't think that's it. And they go, what do you mean you don't think that's it? And they go, I said, well, okay, watch this. I said, here's the board, put it in. Let's raise the temperature to 125. Actually, I've turned it up to 130. And now we had a test point where we knew whether it worked or not. And there it went up to 130 degrees. And they go, oh my gosh, you did fix it. Yeah. So the boss's boss comes in. He's celebrating. We're all celebrating. And what does he tell me? If you quit, I can give you a raise. I go, quit? If I quit, Villanova won't accept my credits from Temple. I took 4 courses at Villanova, got A's in all of them, and they won't transfer any of my credits. If I quit, I'm going to go to college someplace that will accept my credits. And the college was the University of Arizona. So that's what happened, but I didn't know until years later why they didn't just give me a raise. It's because they had given me a raise within the last 6 months, and they only gave out raises once a year, so they weren't going to give me a raise unless I quit. If I quit, then they want to hire me back. So anyhow.
Bill, can I interrupt?
Yeah.
I'm concerned about the last 2 speakers, and we're getting on to 7. So can you wrap it up?
Yeah, I can wrap it up. So what happens is after that, I'm working on the CD660-600 to simulate fusion at the University of Arizona. I'm now using the supercomputers of the day. That, by the way, had punch cards, just like what you were talking about. And then at Motorola, now I'm going to use a computer for everything. And so then I simulated and designed an ECL process, bipolar process, got involved with the 6800. Then I was on the team of the 6502, as you know, and the rest is history.
Bill, thank you so much. Your involvement with Philco is important to us because you know the geography, you know the company, and Paul actually had his hands on a Philco machine. I have been trying for a year to find people who can talk on the Philco. I still haven't found enough people. If you run into anybody who's a Philco Transact expert, I'd like to interview them and include them in maybe next year's World Computer Day. But we're going to jump on over to John Day, who's going to tell us about the ENIAC, the interesting Illinois based computer, and he can tell us about how he got involved in it and about the ENIAC series. And Bill, you have to unshare your screen.
Got it. There you go.
Okay, all right. Here, let me share my screen. And okay, well, Illinois was a little bit different than what I've been hearing. Illinois had established a computer science department by 1964 and graduated their first PhDs in 1967. But they started building computers between the math and the double E department much earlier. Basically, first there was the ENIAC 1, which really quite interesting way this came about. In 1948, Illinois, the university allocated $150,000, to build ENIAC 1. Now, they actually let a contract to a company in New York called Reeves Instruments to build the machine, but they never delivered. They were falling behind. And so Illinois canceled the contract and decided to build their own. And they were first going to copy the IAS machine at Princeton, that von Neumann had been working on. And they were just going to use the circuit diagrams from that, but they got into it and decided that no, it would be better to just redo the circuit diagrams for something, at this, redo the whole thing. So after they canceled the contract, at some point, so they got all that documentation from the director of IAS, Robert, through Robert Oppenheimer, and the physicist Ralph Meager was appointed chief engineer upon von Neumann's design at Illinois. What they did, and right about the same time, the university obtained from the U.S. Army Ordnance a contract to build an identical computer. So what they did was they used the money from the two machines to build two identical machines. The machines passed their acceptance tests in February of 1952. I confirmed here that they actually built the machines, assembled them at Illinois, then disassembled the Ordvac, what became called the Ordvac machine, and trucked it out to Aberdeen Proving Ground to reassemble it. And so basically the machine was 2,800 tubes. It was 10 feet high, 2 feet deep, and 8.5 feet long. Which actually, from what I'd been hearing, wasn't all that big. Here's a picture of it. Now, one of the things that was really indicative of Illinois was that everything they built, the LEX 1, 2, and 3, were asynchronous logic, no clocks. Okay. In fact, as an undergraduate, I had 2 courses in asynchronous logic design. And so, it was a 1024 word memory with Williams tubes, 40-bit words, and then a 12,800 word drum. And then with this, people were asking, what you could do with so little memory. Well, the first music composition by computer, the ENIAC suite, was done in 1955. In 1957, they used the computer to compute the orbit of Sputnik within 2 days of its launch. And they also learned a lot about software engineering. One of the things I remember, hearing about was, they learned not to do self-modifying code. They went to modify the square root routine one time, and so it would just check for negative numbers. And so, they did it. Made the slight change, and the algorithm no longer converged. And you're familiar, you're using Newton-Raphson, you got to seed it with 0.5. Well, they looked at it and come to find out memory was so tight, you wonder how they put so much into small space. Somebody had noticed that an instruction further up earlier in the program was a really close approximation to 0.5. So rather than declaring another word of memory to hold a, the constant 0.5, they just used it to see the algorithm. And so when they stuck in the conditional for checking for negative numbers, they moved it and it was picking up something that didn't look at all like 0.5, and wasn't converging any longer. But most tubes lasted about a year. The Williams tubes about 30 hours. They operated about 8 hours a day, and then they'd have to do maintenance. So it was really, and I've heard a lot of stories about how, they would have to go through and replace tubes, essentially almost every day. It was decommissioned in 1962 to make room for ENIAC 2. Now, a quick word on ORDVAC. There's a wonderful link on ORDVAC, really, very much detailed. I really recommend it. It confirms that the machine was assembled and tested at Illinois and then dismantled and moved. They planned to use circuit designs from the IAS, but ended up using ones developed by Illinois. The programs could be input on paper tape. This would have been how, Illinois actually, once Illinois had the machine running at Belvoir, they were assembling there, so they didn't have a machine they could use. So they actually had remote access to the ORDVAC in Belvoir or in Aberdeen.
I'm watching a webinar that is about the history of computing.
What?
Dan Kotke.
I'm sorry, is there somebody? So, so you could input on paper tape. You could have terminal connected to it. Actually, the first Plato program was also done on ENIAC 1. And then I was told many years ago that ORDVAC had a very long history because over time, they kept replacing parts of the ORDVAC with new hardware that would do the same thing. And in this webpage, I came across, a couple of these. And what was described to me years ago was that the machine kept getting smaller and smaller. And so in 1955, they had a new drum. It was a magnetic drum, was first installed with track selection in 25 millisecond to 3 microseconds access time. They added a magnetic core memory in 1956. New transistor adder was added in 58. And ORDVAC has operated, according to this, for 24 hours per day basis at better than 80% efficiency. And by late 1961, it was scheduled for continuous operation. I didn't see when it was decommissioned, but I think it lasted much longer than that. And there were probably more replacements here, that weren't documented there. So it was really kind of interesting to see. ENIAC 2, though, was the follow-on at Illinois. And it was really, a much more, this one came online in 1963, was the first transistor and pipeline supercomputer, also asynchronous logic. At its inception, it was 100 times faster than any other machine and became operational in 1962. It had 8K of 52-bit words of core memory. Access time was 1.8 to 2 microseconds, 65K word drum, 7 microsecond access. Interestingly, it had a fast buffer, analogous to what we would call cache today. Floating point format was a 7-bit exponent with 45-bit mantissa. Instructions were either 13 or 26 bits. There was a bit of a competition between IBM Stretch and the ENIAC 2, but because Stretch was using synchronous logic, they sort of won out. The asynchronous logic was really pretty difficult and took a lot more electronics to do. During the checkout of the machine, it was used to confirm all of the Mersenne primes and find 3 new ones. The machine was in constant use, even when I got there in 65, 66. and of this, considerable press. In fact, for many years, the U of I post office had a postmark for the primes. Oddly enough, the asynchronous logic could behave, rather erratically sometimes. There was one incident where it took considerable work to trace. The machine would start acting odd, for no apparent reason, and it wasn't all the time. It would happen, maybe periodically for a little bit, and then it would go away for days, and it would come back. They finally were able to track it down to being a 6-cycle pulse on the incoming AC line, which was even stranger. I mean, where was this coming from? I mean, it was really odd. Come to find out, it turned out to be the 300 MeV electron accelerator 1.5 miles away on the south end of campus. And you want to talk about big vacuum tubes. They had a rectifier, an ignitron tube that was 18 inches across and 2 feet high with mercury in the bottom and a diffusion pump to maintain the vacuum. So, that was what was causing it. Well, actually, what was causing it was they had a 0.01 farad capacitor that they were dumping over the machine every 6 times a second, from 6,000 volts to minus 6,000 volts, and generating about 18,000 amps. So, yeah, that's a pretty healthy pulse that was, on the AC line. It was used heavily until it's decommissioned a decade later, and the space became a lecture space in the digital computer lab. Actually, contrary to what we heard earlier, there are over 2,000 pages of documentation on this machine at Illinois. ENIAC 3 was a little bit bad luck. This was a fine grained SIMD machine architecture to do pattern recognition. There was some really interesting stuff going on with probabilistic computing and threshold logic at Illinois during this period. Threshold logic today would be called neural nets. It was initially used to analyze bubble chamber photos for particle accelerators and analyze biological images. I've never found much on the machine. There's probably some, there is stuff in the archives at Illinois. Unfortunately, the machine was destroyed in a fire in 1968 when a Variac shorted out on a woodtop bench and set fire to the lab. Then there was ENIAC 4. So let's just do the facts first, and then we'll talk about how things went awry. Dan Slotnick was the head of the project. In 1952, working for at Princeton, he had the idea for a massive parallel machine. And again, this was an SIMD machine, not an MIMD machine like Thinking Labs. Frankly, none of us really found it all that interesting, but he pursued it for the rest of his life. First at the Solomon, as the Solomon machine for the Air Force, and then at IBM and Aeronica, and then finally at Westinghouse before moving to Illinois in 1965 to build ENIAC 4 for ARPA. An RFP was issued in 1968, won by Burroughs by teaming with Texas Instruments, which is going to prove fatal, to provide new LSI technology for the machine, and push superconductors. The machine was originally conceived as 4 quadrants, each with a control unit and 64 processors. A Burroughs 6700 managed the ENIAC 4 as a peripheral processor. Again, the B6700 was the new upgrade of the 5500, and so it was all new hardware too. So we've got, a new supercomputer architecture being tried out, new chips being developed, and a new control machine all new at the same time. The PEs could act on 64-bit floating point words, 2 32-bit floating point words or half words, and then 4 8-bit fixed point words. Each PE had 2048 words of thin film memory, 64-bit words, of course. The ability to move words one hop with adjacent PE. So it really was an array processor where you could move things, to the adjacent PEs, fairly quickly. Such a large machine was expected to have a fairly high failure rate, so extensive fault dictionaries were also developed. Languages for how you were going to program a parallel machine were developed at Illinois. Two of them based on Fortran and Tranquil, and then Bleipner was based on Algol. The machine was built at Burroughs Great Valley Lab near Paoli. And a new building, contrary to what the Wikipedia page said, called the Advanced Computation Building, was constructed at Illinois, a couple of blocks from the Digital Computer Lab. As you probably noticed, the project was pushing the envelope on many new technologies being incorporated. So it's not surprising that some problems were running. So then there's the saga of ELIAC 4, the intersection of big science, politics, and national politics. First of all, there's the technical problems they ran into. TI had trouble making the chips. So 1 inch board chips, an inch in diameter, became 6 by 10 inch boards. This greatly distorted the machine. It slowed the clock down to 16 megahertz, incurred a 2-year delay. The machine was 10 feet high, and I mean, this was, larger than ELIAC 1. The machine was 10 feet high, 8 feet deep, and 50 feet long. Because of that, because it was synchronous, there could be 10 to 12 instructions, on its way to the PEs. If you took an arithmetic fault in the PEs, you only knew within 10 or 12 instructions where they were, because, there were that many instructions on the line. Now what happened here was TI said they couldn't make the chips on time and needed another year. And at that point, that's when they decided to ditch TI. Now, what I've heard from being on the project was that TI could build the chips, but not for the cost. And so they put their lawyers to work and got out of it. And that's when the machine sort of blew up in size. Also, it was a humongous cost overrun. And so, they quickly downsized the machine from building 4 quadrants to building just 1. But then there were the other problems. When Burroughs went to mate this control unit to the processing elements, they discovered that one group had used positive logic and the other group negative logic. And so they had to suddenly put in a whole bunch of inverters to, hook them together. And if that wasn't bad enough, Burroughs numbered bits from left to right. And so when the CU was mated to the IO unit, some bright engineer thought that high order bits meant the ones with the biggest numbers. In other words, the right end of the word, not the left end of the word. So extensive rewiring had to be done and more. As it turns out, and this was just a very common single, address register accumulator machine, in terms of architecture, it was really fairly pedestrian. The later Burroughs scientific processor, the BSP, really was ELIAC 4 done right. It really felt much more in the Burroughs mold of tailoring, figuring out what the instructions needed to be and what the compiler looked like, and then building the hardware to do that. And it's actually an interesting problem or interesting machine. All of this cost millions of dollars in cost overruns. The project was scaled back to 1 quadrant, as I said. ARPA was becoming very frustrated with Slotnick and the soaring costs, and there was considerable pressure to reduce costs, but little place to do it. Meanwhile, it was the late 60s, the time of considerable turmoil. Civil rights, Detroit and LA were burning, hippies, Vietnam, 68 Democratic Convention, National Guards on campus, the movie Z. that movie was a very powerful movie about the overthrow of the military overthrow of the Greek government. It was playing at Illinois during Campus Town, and one night when the movie let out, people walked out of the movie to find a riot going on the street, a line of National Guard at one end of the street, and champagne cops in riot gear at the other end of the street. It was an interesting time. Not to be left out, there were demonstrations at Illinois. Campus Town was trashed a couple of times. As the largest DoD contract at Illinois, ENIAC 4 became the target. The Daily Illini, the student newspaper, was trying to be a leader of the demonstrations and contended that the project had been secretly brought to campus. After many demonstrations, a debate was arranged between the leaders of the demonstrations and two of the ENIAC 4 OS group, which was our group, shown that it had, and they had actually gone down to the local newspapers and found that all the Board of Trustees decisions by ENIAC on ENIAC 4 had been covered in the newspapers, just not in the Daily Illini. Oops. There was a perception problem here. At GVL, the engineers were the stereotype white shirts and pocket protectors. Us, not so much. To give you an idea, once there's four of us on our way out to Paoli to work on the machine, as we changed planes in Chicago, a flight attendant said to me, "Are you guys in a band?" And I said, "No, we're crypto-fascist lackeys of the military-industrial complex," which is what the student referred to us as. The debate then shifted to no classified, after we pointed out that it had not been, secretly brought to campus. They shifted to, well, there should be no classified research on campus, and we said, yeah, we agree. There's nothing classified about this. In fact, the building isn't secure, and it's not going to be secure. But they didn't want to believe that. After all, if they believed it, then there would be no reason for demonstrating. So, things kept, oops, wrong way, John. Sorry about that. So the demonstrations continued, tensions mounted. The small two-story wood frame building, which was our office, was firebombed. Luckily, it didn't go off. It would have gone up in an instant. Slotnick saw an opportunity, though, in all of this. The safety of ENIAC 4 can't be guaranteed if it comes to the U of I. It is decided to send the machine to NASA Ames. Slotnick gets out from under the cost overruns. The new guy won't take the machine without the money to finish it, but he's the new guy. ARPA loves him, right? Tensions escalate even more. Big demonstration plan for ENIAC against ENIAC 4 made worse as events overtook it. Okay. Wednesday, April 29th, Champagne cops accidentally kill a young black man. The story was that he jumped out of his car and was running across an open field, and the cop jumped out of his squad car, slipped and fell, and his gun went off, and he shot and killed him at 50 yards. Nobody believed the story. There was rioting. The north end of Champaign was burned. National Guard is called out. And to make matters worse, on May 4th, the Kent State massacre occurs. Most universities went out on strike. Things are looking real grim. However, Saturday morning, 9:30, Pete Olsberg walks out on the back porch of the Illini Union and announced that ENIAC 4 was going to NASA Ames, where it did classified research, of course. Diffusing the situation, the demonstration is called off, except the Illinois State Police were a little disappointed not getting to crack heads. So that afternoon, with people flying kites and studying and taking naps on the quadrangle, they surrounded the quadrangle and arrested everybody on it. It was interesting times. And with that, I'll let Gary tell us what happened when it got to NASA Ames.
Okay, let's see. I guess do you hear me, everybody? I think I'm on. Hello?
Yeah.
Yep, we hear you.
Okay, good. Okay, yeah, you've said almost everything that I wanted to say, but I can add a few things. When the machine arrived, they were having trouble getting it up, bringing it up. There was lots of work that was going on. One thing is there was an awful lot of places where there weren't. This was ECL logic, so you need termination resistors at the end of a transmission line, and I guess about half of those transmission lines were terminated correctly, and half of them were not. So that was a big problem. So they had a big project putting that on. And with that, there was a lot of cold solder joints that were made, which was another reliability problem later. Then the next thing that, let's see, then I was in charge of a bunch of ladies that were doing some of that work. I came in late on that game, and they were just about finished doing that. And then I was boosted upstairs. Where the ENIAC upstairs meetings on the main floor, because this work was done in the basement of the building. So on the main floor, I went into the ENIAC room for the first time and saw this thing that looked like a freight train. And I said, "Is that it?" And they said, "That's it." And so I walked over, and the first thing that happened was I saw this guy at the console there that looked like an organ console. It had so many keys on it, and he was punching away very, very rapidly, and he kept saying, "You got it?" And the guy says, "No, have you got it?" And so somebody that couldn't see said, "No, don't have it." And they said, "Got it." And then they froze. And I said, "What?" And I walked up to him. I said, "What's going on?" And he says, "We're finessing the machine." And I said, "Gee, that's a word I haven't heard before. Is that a technical term for something?" And he says, "No." He says, "We've got to realign the connectors with the CPU, the CU cards." Speaking of CU cards, let me show you one. I just happen to have a show and tell here of a CU card. Let's see if I can get it. It's hard to get it all on the screen. I can back up a little bit. You can see it. This is one from the, let's see, what is it? It's it's actually on the card. It says FIO. So that would be pardon me, FIQ. That would be the Q for the FIO. Anyway, it's one of the Qs. That's one of the output Qs. I don't know whether it's I for instruction. It's the instruction queue. Okay, so anyway, then I looked into the situation with the connectors and found out that there were these big boards get slammed into the thing, and then there was two big latches that they pull down to push the board in. And those latches, it doesn't matter whether things made up or not, those latches push the board in. And so some of those connectors that didn't quite line up correctly were getting pushed out. And so anyway, when I saw this was on a Friday. I went over to a guy that I knew from NASA, and I said, "Hey, do you mind coming in Saturday? I think I have a little job. I think I have, and I trust you to do it." So we came in on Saturday, and we pulled out these boards and noticed that the fingers on the boards were tarnished, except for a very tippy end on the boards. And I said, "Well, boy, this looks like a real problem." And so we polished the fingers. We took all the connectors and the back connectors and tried to burnish them a little bit, and tried to seat them properly in the board. And then we had a new rule the following Monday that when you plug in a board, you plug it in very gently, and there's somebody behind there that takes the socket and pushes it onto the board. so that you do it simultaneously. And all of the sockets were sort of mounted loosely after that, just so that they could do that the right way. And then anyway, after we did this, we turned the computer on, and my gosh, it operated for 10 minutes, and that was a record at that particular time. Anyway, that was the first round. The other round, of course, before I came on the scene, was the Terminator resistors, and then after that, they found out that almost all the solder joints that were made on the boards for mods that were made, and there were quite a few, were all cold solder joints, and that had to be. They got in a bunch of solder women from NASA to resolder all the solder connections and to get that good. And meantime, when I first came on the scene, I decided I'd sit down and do an MTBF calculation, and using the best information I had, it looked like the thing would only stay up for 8 hours if it was operating normally. And so I said, gee, this is not a great design. And anyway, but if it at least operated for 8 hours, they could catch errors very quickly. They had a thing called what was that thing called? It was called I had it here somewhere. TRIP. TRIP stood for a triple redundancy error thing, and what they run the program part of it in triple redundancy, and the testing would be would look for the part of the trip that didn't make it, the part of the third part, when they would run through the diagnostics, and then they could nail it really quick after that. So anyway, because they had TRIP, which was a really good diagnostic program, they could find the problem really quick, and then they could pull a PE out, and or I should say pull out one of the donkeys. There was 16 donkeys, which were the PUs, and then each PU had 4 PEs in it. The PEs were, you couldn't even tell where they were. They were sort of all mixed together inside, the wiring, the backplane wiring on all these little tiny cards that were in there. And anyway, the techs knew where they were. I didn't know. That was I lost track of what I was saying, but anyway, that's sort of the sum of it. After that, I was moved up to another job, which was to design a replacement for the iliac, which I did with another, which I was doing with another guy, in the meantime, using a much higher degree of integration and so forth, and not using ECL. Going back to the case in point here, though. Anyway, after that, they decided to do another thing, which was you can calculate these things were so simplistic. The logic, it was very, very simple. So you could there was no great chains of logic. So you could do a curve trace on a particular point, and you could calculate what the curve trace should look like if you were looking on a scope and using curve tracing. And so they decided to curve trace every connection on the iliac, and that project went on for everything can be put on an extender card, so you could actually do that, and they had people doing this curve tracing, and I'm glad I wasn't part of that, because that looked like the most monotonous thing you could possibly do, because they would look at they had on the screen of the scope, they had lines drawn on it that were the curves that you would expect, and if it deviated from those lines very much, you knew that there was something wrong with that circuit. So anyway, they were off doing that, and I was off with Dave Stevenson designing a replacement iliac, and then the whole thing came tumbling down because Mel Pirtle, who was running the show, got fired over some money issue. I think it was like $1 million or so that sort of got lost in the works. So Dave Stevens and I decided to leave the company and do something else. So that was sort of the end of that story.
Gary, wow, it's so amazing to hear all the challenges and all the work, the labor,
Enormous amount.
enormous amounts, and the money. I think that was the most expensive computer ever built, based on some metric. I'm not really sure what, but John Day can comment on that, and then we'll go to Q&A for everybody. Go ahead,
Well,
John.
Yeah, there were a couple of questions in the chat. One, there is stuff on asynchronous logic at Illinois. There was a fourth machine built called CSX. I've got a couple of papers, but nothing in electronic form that I know of off the top of my head. Somebody mentioned that iliac was the inspiration for HAL. There are a couple of good stories. There were a lot of good stories that came out of all this. I won't tell the one about the Are You Guys in a Band thing. That was just the beginning. It got a lot weirder. But anyway, one time when like 5 or 6 of us were in Paoli, around Paoli, to work on the machine, there was one, we couldn't get the machine one night. They were down for maintenance or something, the 6500. We were using the serial number 2 of the 6500. So, here we are, we're stuck in, out there, 6 of us. And so, well, what do we do this evening? We can't use the machine. So we said, well, what about a movie? Okay, so we look around. Well, there was a strip mall on 202 between King of Prussia, where we were staying, and the machine that we went by, that had a movie theater, and 2001 was playing. Well, we'd all seen it, of course. But, it's always fun to watch Mating Spaceships. And if you remember, 2000, at the end of 2001, there's this light show that goes on for quite a while. And, a lot of people, back then used to get stoned and go see 2001. Well, we're paying cool, we're on travel, so we don't do that sort of thing. So, so we go to the movie, and of course, as you know, HAL was built in Urbana, Illinois, where the University of Illinois is. So when it comes to that plug, we all applauded, right? Normal thing to do in those days. So we, the movie ends, the house lights come up, and we start to leave, and we come across this row of freaks, stoned out of their gourds. Right. So we stopped to talk to them. We have a little chit chat and everything. And where are you guys from? Oh, we're from Illinois. Oh, you're the ones who, applauded when they said, HAL was built in Urbana. Yep, we're the ones. Well, what are you doing out here? Oh, we're building the world's largest computer. You mean like HAL? Well, sort of. And we left. And I figure these guys go back, and tell their friends, hey, man, we met the guys building HAL at the Phoenixville Cinema. And nobody ever believed them. Oh, man, you were just so stoned. You were imagining this. You hallucinated it. Okay? But
Love the story.
Never convinced anybody that they met the guys building HAL at the Phoenixville Cinema.
John, I love it. Great stories. This is just what we want to do on World Computer Day. Think back and reminisce about the good old days, but really dig deeper on the technology and the arc that it has to bring us where we are today. The floor is open to anybody. You can raise your hand in Zoom, or you can post it in the chat box. And if you're going to speak, just raise your hand and unmute yourself and just blast in. Go ahead.
So Actually, if somebody wants to know more about asynchronous logic, send me an email at day@bu.edu. Okay.
Thanks, John.
Okay. All right.
I am drinking a Youngling, and I'll hang out with you all as long as you want on World Computer Day.
Oh, one other comment. One of the things I've found about history, especially as we get into some of the newer stuff, is because I've been doing research on some other aspects of the history of computing, and I also do history on 17th century China. The historians have a problem in that they don't really understand the technology that well. And that starts to get in the way. So, I'll leave it at that.
A lot of it's in here.
I'm sorry?
I say a lot of the history prior to the Cray 1 is in these two volumes.
I see that Supercomputer 1 and 2.
Pardon?
I see that. That's very good.
Yeah. I'm going to give these to a computer museum that doesn't have it. I don't know who's in charge of a computer museum here.
I will gladly accept it as a donation to Compuseum, and we'll take good care of it.
I want to make sure it gets to a place where it has use.
Good. Well, we'll help you with that.
Okay. We'll get that offline.
Yes. Others,
Oh.
raise your hand. You can raise it like this, or you can do the one in digital. Just unmute yourself and send out and blurt out your question. We're happy to have it.
Yeah, I have a copy of one of the posters. Why this thing is? Well, let me pull it back. Smash the. It was one of the posters that was in Illinois. That to try to. I forgot who was mentioning all the problems of the ENIAC. But this is one of the posters. This is not the poster. This is a copy of something I found on the internet. It was a copy of the poster. And
well, I had that in my presentation.
Yeah.
Yeah.
Oh, you had the poster?
Oh yeah, I've got an electronic form of it.
Yeah.
Yeah. Yeah, that was what I was talking about. That all that
Yeah.
came down right after Kent State. It was a pretty dicey time.
Well, if it didn't happen, then I wouldn't have had the pleasure of messing around with that machine.
Well, no, I mean it provided, the riots provided the excuse for Slotnick to get out from under.
Did you have anything to
That
say
may be
about
another.
I'm
They may
sorry?
have actually helped that too. Yeah.
Yeah.
Do you have anything to say about the ENIAC music suite?
No, not really.
So actually, those people, the ENIAC fanatical fighters, or whatever you want to call them, actually probably helped get the ENIAC come to fruition. Because if it didn't go out to California, it probably wouldn't have never been finished. Possibly.
Yeah, because ARPA was getting tired of pushing money to Slotnick, and who knows? And also, given what you've said about the state of the hardware, and having watched people work on the control unit backplane, it was bizarre. I'm not at all surprised.
Well, actually, the missing $1 million, of course, is an interesting thing on our end of the thing here. There is an interesting footnote now that Mel has passed away. After being fired, he bought a yacht and sailed the Pacific with 4 women. They were to help put up the sails and so forth. It was a sailing yacht. He needed a crew.
Oh, on the ENIAC suite, Illinois was a big center for electronic music and also just avant-garde music in general. We were, a lot of that stuff got done. John Cage was in residence there for 2 years. My best friend was worked for him at the time, and he staged two big happenings at that time. And at that time, Illinois was would do a festival of contemporary music every other year. So there was a lot of that sort of stuff going on all the time. And actually, we did a concert of that in the advanced computation building at one point because we were collaborating. Well, the head of our operating system group's only degree was in composition. And so we were collaborating with the music school and things at the time. And we had an electronic music and also non-electronic but avant-garde stuff concert in the building at one point. So it was collaboration across departments is really one of the earmarks at Illinois, and they've become aware of it. It was really just sort of, early in those days, but it was quite common. Let's see what.
I think the ENIAC suite, the music that came out of Illinois, was quite.
ENIAC suite was the output of a program on ENIAC 1.
It was ENIAC 1 because
and
it was actually quite a good piece, actually.
Yeah, no, it's a very interesting piece, and
suite for ENIAC, and it was 1969. It was very early.
Oh yeah, 51. Yeah, so it was the early 50s. No,
I don't think it was that early, but it was.
No, the machine came online in 52, so it was like 55. Well, I said 55 in the slides. Yeah, the ENIAC suite was done. And there was more electronic music after that. There was the Illinois has a museum of music, and one of the machines that was built for composing electronic music is in that museum. They also have all the papers of John Philip Sousa. It's a whole different story.
Wow.
But electronic music was, not just generated by ENIAC 1 and 2, but other things as well.
Well, the other side of that whole thing was happening at RCA, where they were doing this electronic, but also, music 1 and 2 and 3 and 4 and 5, and those music programs were all being written in the 50s and 60s.
Right.
During that time. So
well, the thing that it's in Shannon's theory of communication book, that that frequency of characters are unique for a language, and you can generate strings that look like that, and pairs of characters and triples of characters, and get things that begin to look like words and stuff like that by just generating with a random number. For the John Cage stuff, they actually did that with Mozart. And this friend of mine played some of that for me at one point, and it sounded like Mozart. It didn't go anywhere. It didn't really develop, but it sounded like Mozart.
Yep. And now that wraps quite around to what's happening today in the so-called AI, where they've analyzed all the music, and now they can interpolate, and they can invent something that Mozart would have written, maybe, and it can
and paint like something Van Gogh would have done, and so on. Yeah.
It's sort of like it, but there's no inspiration. It's just imitation.
The thing that worries me about this is, has the technology really advanced, or is the compute power finally there?
I think it's more like the compute power is there because the stuff that comes out is fairly creative, actually. You just sort of give it parameters, say, I'd like it to be sort of like this, but you can mix it with some of that, and you can get a result that that is, pretty responsive, pays some attention to what you said, and comes up with something that's very reasonable.
Yeah.
I'm not saying that it's a Mozart or a Shostakovich or anything, but some of it's not bad, and I think we're like maybe we're less than a mile away from being having computers that are a hell of a lot smarter than we are, not just in speed.
Yeah, well, beyond the speed, I really feel like one of the big issues is we now have so much data that we can suck up, right? A lot of these generative AI models have been based on just looking at petabytes of data, and it's being able to like throw ridiculous amounts of compute power at this incredibly overblown neural network construct pointed at this steaming trash heap of data that we're able to produce things that are somewhat interesting and familiar. I think we have a long way to go though before, I mean, particularly given all the issues there are with AI having hallucinations and tending to be most certain when it's most wrong. I think
Well,
we have.
on the other hand, I think they ought to be able to use AI to clean up AI, clean up the database. I mean, it seemed like you could turn it on itself.
I have my doubts about how smart it can be, because I submitted 6 of my exam questions to ChatGPT and it's scored a 40.
Only 40. That's
Only
not
Well, you're maybe I would score 10. I don't know.
Well, my
Maybe
students
you're a tough guy. Tough exam.
must be.
Yeah.
I don't know. That I see, a lot of what people would call creativity, and a lot of the responses that you can get from the computer intelligences that we have currently, and they're only going to get better. They're not going to get worse. And they're going to try to make databases, I think, that are cleaner and that'll help clean up some of the nonsense that you get there. I mean, I haven't seen a first grade physicist come out of or mathematician come out of this yet, but you never know. It's certainly better than the average intelligence of a human being at this point.
Yeah, that's shocking, isn't it? Yeah.
That's scary.
I mean,
Well, we're getting there. It's hard to compare it to the most exceptional people that we have in the world. It's like, yes, this isn't Mozart. Well, and neither are you. Neither are you, and neither are you. Nobody's Mozart.
There's a real problem here, because we're trying to take this computer and say, I want you to compose music like Mozart and or be better than Mozart. And the computer is a general purpose thing. It's got this database and it's got Mozart music, but it's just a general purpose thing. It's not wired like Mozart. So that may be part of the problem. You have to be wired by Mozart to compose the best Mozart pieces.
Yeah, well, people forget that there's a lot of humans that can do this too. There's a lot of humans that, if you say, well, can you make something that sounds like Mozart? Yes, they do that. And they put it in the soundtracks of the movies. Can you make a voice that sounds like the president? Yes, they do that. Humans can do this all day long, to imitate what has been.
Some humans can.
Yes, a lot of them. Yeah, yeah.
There's a contest every year
But
for
the people who
indicating
treasure are the ones that make something original, and that's the hard thing.
Anyway,
I know none of us want to think that we're ready for the retirement thing as far as retiring from being human beings and not let the next generation of computers take over. But it's going to happen.
Folks, I could keep this going on forever, but I do want to thank everybody who was a speaker. It was a really inspirational thing. We've gone almost for 3 hours on a 2-hour event, and that shows good things. It says the audience was interested. We had 50 people on the thing from all over the world. It's really quite impressive. It was a deep dive in a lot of things. I could have gone hours on any one of those devices. It was so enriched. So I want to thank you, and especially Mike Jones, the moderator from the System Source Computer Museum down in Hunts Valley, Maryland. He did a great job. The Zoom session stayed up. Things moved smoothly, and there were plenty of good questions. I think I'll shut this down in, let's say, 3 minutes. If there are any last pressing questions, please ask them. I'm especially happy to see Dick Moberg and Bill Mockley and people who've come to the Swine and Swill pig roast in the summer. You're all invited to that. I encourage you to go down to Hunts Valley, Maryland and see Bob Roswell and his beautiful System Source Computer Museum. It will blow your socks off. Each person on
We're always growing.
Always growing, yes.
Sounds exciting.
Each person.
And I want to turn it around and point it to you, Jim. Thank you so much for putting this all together. It's really impressive, and you've done it multiple years, but this was really nice. And so, hey,
Absolutely.
for putting together.
Happy birthday.
Thank you, Bill. I think it's a great compliment coming from you. Happy World Computer Day 2024. We have 2 years to go. We're going to have the 80th anniversary of the ENIAC. So we'll have a big blowout again on ENIAC. And just to let you know what we're thinking about for the 80th anniversary of the ENIAC is to have Kathy Kleiman take the lead. And we're going to talk about all the ENIAC women and make that be top front on the 80th anniversary of
That's
ENIAC
awesome.
Day at ENIACday.org 2 years from tonight.
And Jim, I don't know if you remember that you have a big vacuum tube cake behind you as your background, but one of them is blown out, and I think you need to blow out the rest of them and put this to a peaceful end. Thank you.
It could have been the Youngling beer, but I thank you all. I'm going to shut us down now. Mike Jones, again, thank you so much. We'll
take
have
care,
a
guys.
call as a wrap-up call probably next week. Thank you again.
All right. Thanks,
Thank you, everybody. Thank you.
Happy
Bye-bye
World
now.
Computer Day.
Thanks, Jim. It was great.
Thank you.
Bye-bye.